Great. Well, welcome everyone. Thank you so much for having me here again. It's my pleasure to speak to you about my research. And tonight I'm hoping to keep a general theme of talking about the components of our galaxy and a couple of physics insights about the cosmos that we can grasp from them. So I am going to start with the position of our solar system in the galaxy. So we are located in the Sagittarius arm right here. And this is an artist's rendition of what the galaxy would look like, because we cannot actually go and take a picture of it since we are inside the disk itself. But in general, we believe that most of the galaxy is made of stars, gas, and dust, with large black hole at the center of it and potential tinier black holes that we haven't yet detected that may be in the galaxy somewhere. And in addition to, so we call these guys baryonic matter. In addition to those components, we know that 95% of the mass of the Milky Way is actually made of dark matter, and that the galaxy, as we usually represent it in terms of baryonic matter, is located at the center of a dark matter halo. So I'm just gonna go a bit through the components through my talk, and talk about each of them and how they connect with other physical processes. So interstellar dust, we are still trying to figure out what interstellar dust is made of, but we think it's composed of at least some part silicate, some part carbonaceous type of substances, molecules, and that the sizes of these dust grains can be between hundreds of nanometers and micrometers. And dust is quite essential in the process of both star and planetary formation, and it also ties into the magnetism of the galaxy, which in turn is a factor that affects the cosmological studies when we try to make any measurements of radiation coming from outside of our galaxy. So this is a picture I took with my camera when I was at an observatory in Chile. This is just with the camera outside, not through the telescope in any way. I was at a 4-meter Blanco telescope, but I tried to set the exposure to be similar to what I was seeing with my own eye on the sky at the time. So why I hope maybe you can see it on the screen on the projection. I'm not super sure how the lighting looks there, but you can basically see the galactic plane in this picture, and there's this dark spot over here. That is a dust cloud. If dust clouds weren't there, the galactic plane would actually look way more homogeneous in terms of just a very clear distribution of stars on the sky. So we actually are able to see with our own naked eyes the dust in our galaxy when we look at the sky at night, because we see these dark patches. And this is how they look on the whole sky in a more exposed sort of picture pieced together by some very proficient amateur astronomers online. And these are basically the dust clouds in the galactic plane. So how do we normally characterize the interstellar medium dust? Well, there are two big ways. One is through the extinction, which is the process by which dust blocks light coming from behind it from other stars that are located along the line of sight, as you can see in this this picture. So we can use this to our advantage in the following way. If we wanted, for example, to infer where the dust is in the galaxy, we could use stars. And nowadays we have access to 6 billion stars and their information. So it's what we call a big data. And it's becoming even bigger as the Rubin Observatory is coming online. And the SDSS, the galactic mapper, is also going to target the Milky Way basically in a program called the Milky Way mapper. But the principle is pretty simple. We can look at stars that are aligned along the line of sight, like the 3 stars here, and each of them have a certain amount of dust in front of them and in between them. But what we actually observe from the Earth is we see the stars having been dimmed a little, and in particular, they dim more as there's more dust along the line of sight. So what we can do is, if we knew how bright the star is, then we can subtract the difference between its brightness and infer how much dust there is in the first section, and then look at the second star, and then subtract the first dust and conclude the amount of dust in the second section, and then in the third section. And using this procedure, we can basically map the density of dust along the line of sight if we have the stars and we know how bright they should be, and then we measure how they appear. Of course, in reality, all the stars are different. They have different brightness. There's no standard candle in a galaxy that we can use for this, but we can still infer what they should have been because of their spectral information and metallicity. So there are stellar models that if you give those models enough measurements of the stars in different magnitudes, they will be able to infer what the stellar type of the star is, and that gives you what the luminosity should have been, and that gives you what the magnitude should have been at that distance. And we know the distance to the stars using the GAAC satellite. So even though they're different, it's the same principle of like we will be able to use their dimming, what we call the reddening, the differential dimming in different wavelengths, to calculate the amount of dust. So a couple of Bayesian algorithms later that we don't have to go through right now give us this detailed 3-dimensional density measurement of the dust in the interstellar medium. So here we are looking from the perspective of the Earth in the direction opposite from the center of the galaxy. So you're looking this way with an angle of view of 90 degrees. So you're seeing a cone of the galaxy like this, and you're seeing the entire distribution of the dust in the interstellar medium in the galaxy. The map here reaches all the way to basically 20 kiloparsecs. So it's going outside of the galaxy here. So this is not a simulation. This is an actual measurement. This is where we believe dust is. And this was done again, having been able to take the measurements of the spectra of the stars that were basically along the line of sight at many different points in the same direction. And that's how the dust was inferred. So this is work done by Gregory Green, who graduated from Harvard in 2019. So the other way that we study dust is through its thermal radiation. So dust emits thermal radiation the same way that our bodies do. This is why the military can see us through the buildings with the special goggles. We peak in emission in an infrared, not in optical. So it's not we're not seeing each other because we emit light to each other. We are seeing each other because we reflect light to each other. But we also emit in the infrared. So that passes through the buildings, and that's how we can see each other. Dust is a bit colder than we are, so it peaks more like in the microwave. So it overlaps with the cosmic microwave background measurements. So that's one reason why these sort of studies are very important, because we can characterize the measurements from the CMB better if we knew what the dust emission is as well. This is a map of the dust thermal radiation over the whole sky. And it's from the Planck satellite. It's a satellite that was designed by the European Space Agency to study the cosmic microwave background in very high precision to try to measure inflation. Well, it didn't get quite precise enough, or rather it eliminated a lot of the models of inflation, but they still didn't detect a signal from inflation, partially because dust was obscuring it. So basically removing dust and characterizing it is like a pretty important part there. But what this means for me as a person who wants to look at the components of the Milky Way is that these data sets are very sensitive to dust itself. So I can use them to characterize the dust in the Milky Way. So these are the 4 higher frequency bands from the Planck satellite, together with the 3000 gigahertz band from the IRAS-Dirbe satellite. This is a 40-year-old satellite, the IRAS-Dirbe. They went up on Kobe. So it's old goodies that work very well. And using those 5 maps together, I asked myself, okay, so I have the dust emission maps in 2D, and I have the reddening or dust density maps in 3 dimensions, and can I combine them together to basically infer other properties of the radiation of the dust, maybe even make a temperature map in 3 dimensions? So the dust density map has density information in 120 distance beams, the one you visualized before. That's the fine sampling of the dust along the line of sight. The beams are logarithmically spaced, so the resolution degrades over distance. It becomes chunkier and chunkier. And this is the sky coverage. There's data missing here because the spectrum of the stars relies on data from the Pan-STARRS observatory, which is in Hawaii. So they couldn't see this part of the sky from Hawaii. But there's studies being done nowadays that are going to fill in this part. So that's okay for the future, not a problem. And this graph here shows the reliability of the map, of the dust map, in how far along is it reliable for. So it's in kiloparsec. The farthest away distance that it works for is 20 kiloparsecs. It's right above the galactic plane. In the galactic plane itself, right through the center of the galaxy, it doesn't work so well. It only works for about 2.5 kiloparsec. The reason for this is that we use stars, right, to infer the dust presence. But to see stars, we have to not have a lot of dust to begin with. And in the galactic plane, after you go for a long time, you have so much dust that you can no longer see the stars themselves. So then you can't do the whole algorithm. So that's why it's very bad over there. And as you go above the galactic plane, where there's still a lot of stars, is very good. And then once you go into the north part of the sky, the number of stars just decrease because there's no stars in the galaxy. There's less stars at those latitudes compared to the closer to the galactic plane. So basically, there's this golden zone here at the mid latitudes where the technique works very well. So I wanted to map basically the radiation of the dust from 2D into the 3 dimensions. And to do this, I basically assigned each layer in along the line of sight a different temperature. And there's like 3 parameters that model the emission of the dust. And there's a fundamental degeneracy here, which is, okay, if I want to reproduce an emission in 2 dimensions that's summed over the whole column of dust, the emission can come from cloud of dust that's not so cold but is very dense, or it can come from a dust of cloud that's thinner but very hot. So I know where the density, which density each cloud has, but how do I assign a temperature basically to each of them? So the algorithm breaks this degeneracy by saying, I'm going to look at a pixel that has an area larger than the data set itself. So I have finer resolution here from the data, both in emission and in density, which are the blue squares here. And then I say, oh, the pink square is going to represent the resolution of the temperature map. So there's going to be a single temperature over the pink square, but it's going to have a different temperature in the line of sight. So if the square is big enough, it can have the clouds of dust not aligned with each other. So there's parts of the dust cloud that are aligned exactly here, like they overlap perfectly, but there's also parts where there's like no overlap. So then the algorithm can see, oh, in this part, it should be some an amount of radiation, and it should have a certain temperature. In this part where this cloud is alone, it should have a certain temperature, and then the summation should have a particular temperature, and that's how it basically discriminates between the clouds and is able to assign temperature along the line of sight. So this means that the temperature map is going to have a lower resolution than the resolution of the data we started from. But we start from 5 arc-minutes resolution, which is pretty great. And I degraded to 27 arc-minutes for the temperature map. and it still looks very good. Basically, that's having the resolution of the moon, but there's a lot of moons that fit on the sky when you start putting them in a single line. So it still works. This is just the math for that. It's just, again, a Bayesian analysis where you sum over the emission for each pixel on a line of sight compared to the data. And here you can see the reconstruction of the emissivity. So on the left is the data from the Planck satellite, and on the right is what the algorithm is giving me. After I take the density map, I tell it what temperature it should have. It tells it, and then it sums over it and tries to compare it with the Planck data. So if you have very good eyes, you can probably tell that, yeah, these maps are matching well, but the one on the right actually has higher resolution than the one on the left. And the one on the left is the one I'm trying to reproduce. So how do I end up having higher resolution, right, than what I started from? The reason is that the density map has a bit higher resolution than the emission map, and the density map is embedded in the calculation on the right, which is good news. It just means, okay, we can do basically better analysis, but we want to make sure we're comparing apples with apples when we're running this algorithm. So I degrade the resolution so that both of them can be matched properly. And I check that by taking the differential and making sure there's no ringing. If there was a resolution mismatch, there would be ringing here. So that works. And then I obtained this three-dimensional dust temperature map. So the density represents the density of the dust, and the coloring here represents the temperature. So blue means hotter dust around 30K and above. 30 Kelvin is hot in my world where I work at. And red coloring means more like 10 Kelvin, and green is more like 18 Kelvin. And there's a couple of things that we can see here. Well, first we can see that there's a ring here, ring structure in 3 dimensions, almost like a sphere almost, that is made of hot dust. So this is probably because that used to be a supernova over there that blew up, and we're seeing the gas clouds having been pushed outside in a symmetrical instance. That's why it's like spherical. Other things that we observe are these areas that have both red and blue patches together. So these are characteristic of star formation regions, because star formation regions, are very hot because they have stars that are just heating up the dust, but they're also having cold dust because they have a lot of dust in them, and some of the dust gets shielded by dust itself, right? So you see these parts where, like, basically is what we would expect from a star formation region. And other things that we can see is that these structures with basically star formation region patterns can be seen all the way in the back. If you can tell from the movement of the camera, that gives you a perspective. Like in the back there, we can still see basically the star formation regions existing, which is very cool because nowadays we don't know where star formation regions are. So like we have some information in 2 dimensions when we see some radiation from Bremsstrahlung, so like free radiation, we can see that there should be some star formation region in 2D, but we do not know where in the line of sight is. And this map can actually basically tell us, okay, I'm looking at it and I'm seeing something there. Does it match the radiation I see in 2D? Then that means we probably have an answer to the location of the star formation regions. So it also tells me that the algorithm is working because there's dust here right in front of it, and it could have said, oh no, this dust is very hot. It didn't have to assign temperature to the one behind in the back. So basically the algorithm is saying, no, I'm not going to make this dust hot. I'm going to make that one hot because that's the one that fits the data as it should be. And if we look at known star formation regions, so these actually match up with what we see on the map. This is the Orion A and Orion B star formation regions, and the Tauri and the Perseus and the California ones. So this was basically good news. And sorry, need to get it to move. Why is it not moving? Yeah. So the other good news is that there exists upcoming experiments that are called CMBS4 and CCAT that are going to have measurements of the sky that are 5 times better resolution in terms of emission. So I will have emission maps to work with that are basically much better and will allow me to make the same map with the same procedure with just 5 times better. So this is very exciting in that perspective. The current map has a resolution of 27 arc minutes, so we can envision going all the way to more like 5 arc minutes. One interesting application I wanted to try is that I wanted to see if I can actually calculate the temperature of a known dust cloud that has 2 components. So I wanted to see, okay, what temperatures that the algorithm assigns to that cloud. So the Cepheus cloud is a cloud that we know has 2 components close to each other. We know they are there because when we look in reddening, we can see this knee forming along the line of sight, which indicates the presence of the cloud exactly where the knee is happening. So there's 2 knees, and that's basically 2 components of the cloud. So in my algorithm, I just isolated those components into each of them into into a part by itself with a separate temperature. And I ran the algorithm, and I was able to show that the first component and the second component have distinct temperatures with 3 sigma precision. So that's pretty encouraging in terms of you being able to use the algorithm for actual science. And the other question I was curious to see is like, okay, so now we have idea a bit of like how the temperature of the dust varies along the line of sight. But can I actually kind of connect to what has heated up the dust to begin with? So we believe that it's mostly stellar radiation and the far infrared that heats up the dust. And we now have information on stars in the galaxy, right? That's kind of where we're starting from, but we have emission from stars as well. I never used in this algorithm anywhere the information that comes from the emission of the stars in terms of how much they radiate. But I have an undergraduate student who started working with me last summer, Joseph Tang, and he was really curious about this program. So he wanted to map all the stars that we can get onto the 3-dimensional dust temperature map to see what we can infer from that. We will see a correlation between where the stars are and where the dust is hotter, or is this just a random thing and we can't really see it. So he took the 6 billion stars from the Gaia satellite. This is not an easy thing to work with. It's a very big data set, and Joseph is really, really well handling it. But what he started from was he was looking at a 3-dimensional pixel along the line of sight in a region of star formations that we know of, for example, and he counted all the stars that are there in the specific volume and looked at their temperature as well, and created like a tracer method where he was just summing over the temperature of all those stars there to the power of 4, kind of tracing the luminosity, and then made a map of it, and then looked at the 3-dimensional dust temperature map in that slice. So these are different resolutions, but if you just look with your eye, you can kind of see that, okay, this is hot dust, the yellow part is hotter. It's here and here. And here in the left one, the stars, we can see that there's accumulation of the stars over there, just with the eye. So that was a good sign. But still, there wasn't one over here, for example. And there's other cases where the dust was hot, but there was no stars there. And the reason is because this method only considers the stars in exactly the same position where the dust is. But dust can be heated by stars that are not in the same position where the dust is. It can be heated from far away as well, because stars can be very bright. Just like we as the Earth are heated from the sun, we don't have to be in the sun to be able to be heated by it. So then he started calculating the interstellar radiation field coming from all the stars, basically. So he defines a sphere of 100 parsecs, which is quite large. So it's basically saying that we are calculating the radiation on the Earth that's coming from, you know, not Alpha Centauri, but like way beyond that in terms of like 3 times farther away than Alpha Centauri, or more, something like that. No, wait, not 3 times, 30 times further away than Alpha Centauri. So it's completely like beyond any kind of doubt that this is actually capturing all the radiation that's being hitting there. So that's a lot of stars, but so the algorithm, you know, needs to calculate a lot of things. Basically, select the stars and then calculate at each point in space their collective radiation. So we wrote a very efficient code together to do that, and he was able to create this interstellar radiation field on the left. So now we see that, oh, actually over here there was another source of radiation that can explain this, you know, coarse heated up dust there. Well, first of all, this thing that he did is actually the first time that anyone has calculated the interstellar radiation field using actual information from stars, like actually taking all the stars we know, propagating the radiation to a point, and calculating everything in 3 dimensions. So this is a you know, very exciting line of research. And he ran a correlation algorithm over these matrices that represent the data. And basically, it's you know, it's showing correlations, and it's showing a tighter correlation when he calculates the interstellar radiation field, which is what would be expected. And just wanted to mention, this is a 3D correlation. And this did not have to work because the temperature map of the dust map was not made using any information from the star's radiation. This was a completely independent test of like, okay, I have the emission from the dust. I'm going to map it in 3D. Does it correspond to the radiation of the stars, which should in theory correspond to it? So it's working. It's basically validating the actual making of the 2-dimensional dust itself. And this is an image of the interstellar radiation field that Joseph is calculating over the whole sky. So this can have infinite resolution because it's up to the researcher to choose how fine a point they want to sample it on, because it's just a calculation of all the stars put together at that point. So this is actually very cool. I really like it. This is at a specific distance, at 0.27 kiloparsecs, so like 270 parsecs away in the galaxy. This is what the optical photons would be hitting you on. So you can tell if you want to be, at the beach, or you want to take a nice jacket with you before you go to these locations. And the next part here for this project would be to actually calculate the radiative transfer of the stellar radiation through the dust. So you probably thought to yourself, okay, but you took the stars and you calculated the radiation, but isn't there like something that blocks it, like dust clouds all over the galaxy? Well, they are. So basically, we call that the next order approximation, is to actually propagate these photons through the dust clouds that we know of, and calculate how much of it will be absorbed in each direction. It's a PhD thesis. So we'll see kind of how that works in the future, but it's a pretty exciting path. So okay. So the question here, one of the questions here is, what could you do if you knew exactly what the optical and infrared radiation in all directions is at each position in the galaxy? Like, what would you use it for as a researcher? Like, now you know all this radiation in 3D. I mean, apart from being able to, check the weather when you travel, basically. Apart from that, you could also take advantage using the NASA SPHEREx mission. Also, let me know if you have any ideas about this, because I've just kind of started thinking about this. So I have 2 applications, but I'm very excited about other applications for this. So NASA SPHEREx mission is what we call a mid-class mission in terms of budgeting, that is flying out next year. So this is happening. It's all, approved, constructed. It's going to fly. And they are hoping to map this emission that comes from these organic molecules called polycyclic aromatic hydrocarbons. They are a type of dust, but they are a small grain of dust. So they're so small, in fact, that they do not thermalize. So they get excited every time a photon hits them, and they emit again, and they emit at a particular frequency, and NASA SphereX is going to target that frequency specifically, and it's going to see the summation of that emission along the line of sight in 2 dimensions. So we're going to get just a 2D emission of these organic molecules. But they get excited by photons specifically that are in optical and infrared. So I will have a map that tells me where the photons in optical and infrared are in 3D. So what I'm hoping to do is I'm hoping to deconstruct, inverse the problem, and basically infer where the molecules were in 3D when they managed to create the specific 2-dimensional emission that the SphereX is measuring. So this can potentially be the first 3D density measurement of organic molecules in our galaxy. And this has some implications in general for the whole carbon cycle evolution of star formation because they have so much carbon in them. So kind of nailing the details of these organic molecules is important for that application as well. The other thing that one can do with a radiation map like this is search for dark matter. So dark matter has many different types of models, but there are some annihilation models of dark matter that create gamma rays, and people use the Fermi LAT satellite to study diffuse gamma ray emissions coming from the galaxy. And another source of gamma rays in the galaxy comes from the scattering of the light in the interstellar radiation field by inverse Compton scattering of cosmic rays. The cosmic rays are, very highly energetic, very relativistic moving, basically protons or something like that, or even electrons. So like these guys just hit the photons from the stars and bump them to the gamma ray regime, and then they become polluting when you try to disentangle if there's a dark matter annihilating each other. So you can basically help these calculations by actually knowing where the optical radiation from the stars is. Okay, another project that is a cool thing to study is the correlation between the 3D dust temperature of the galaxy and the other properties of the interstellar medium. So the interstellar medium has these phases that are kind of broadly defined into warm ionized medium, which can be traced by the H-alpha emission. So there's a survey called WAM that basically did H-alpha surveys, and these surveys are actually in 3 dimensions. You can kind of map them along the line of sight. And also the neutral hydrogen is a tracer of the neutral medium. And these surveys are also in 3D because of the Doppler shifting of the line of the neutral hydrogen. So my student, Hanish Kanda, is right now looking at correlating these 2 data sets with the 3D dust temperature map to see if there's any relationships, like are the areas that are more, have more neutral medium, have colder dust, or is the, if the warm ionized medium characterized by hotter dust in 2 dimensions? These are questions that we don't yet know, though maybe we have an intuition what we expect, but it hasn't yet been shown. And then another important application comes from the galactic magnetic field. And here there's a pretty cool trick. So light has intensity, but also has polarization as a property. And the polarization of light is actually what's being measured by a lot of the cosmological experiments that are trying to measure inflation, because inflation leaves us imprint in the what we call the B mode polarization of the light. So dust grains are considered to not be spherical, but to be elongated. And elongated dust grains are known to align with the direction of the magnetic field. And in this process, their emission becomes polarized in a way that correlates with the B field at the location of the grains themselves. So the formulas that connect to the polarization as being measured on the sky basically have the intensity of the dust of the emission that I already have studied in 3 dimensions when I did this map. And the other coefficients can also be looked at if I introduce the measurements from the polarization as well, which we have right now. So I'm just working on it, and I'm curious to see if I can actually probe the magnetic field itself. This will be a probe of the B field in the plane perpendicular to the line of sight. So it's kind of a morphological probe, not an absolute magnitude probe. And the lucky thing here is that there's other probes of the B field that can be combined with this one that will allow us to actually get the whole picture of the magnetic field. So Faraday rotation and synchrotron radiation and starlight polarization are independently being pursued right now by different telescopes around the world. And once we get all of 4 of these guys together, we will be able to make a 3D morphology of the whole galactic magnetic field. And that's would be the first time this has ever been done. So using all these, especially the B field measurements, we can go back to the idea of being able to trace all the radiation coming from basically through the universe. So we can take advantage of the fact that the speed is finite, and basically whenever we look farther away, we look earlier in time, and using this idea, we are probing the whole evolution of the universe. And the only problem is that, if you want to go all the way to the beginning and measure the cosmological, the cosmic microwave background, we are here. So those photons have to pass, first of all, through all the intergalactic medium, but then also to reach us here, we are in the galaxy. So they have to pass through the galaxy itself, which has interstellar dust, which you kind of want to clean and not leave it sitting there so that you can actually measure these photons. And there's this phenomena called frequency decorrelation. This may be a bit kind of a technical definition, but it refers to the fact that telescopes who are trying to measure this inflation have different frequency bands, and they use a specific frequency band to be dedicated to the studying of the dust. And then they say, okay, in this frequency band, the dust is the brightest. We're measuring it very well here, and we're going to correct for it in the other frequency band. And this is called frequency correlation, because you're correlating the amount of dust in one frequency band with how it's going to behave in the other frequency band. But in reality, if dust is actually very complicated in the line of sight and it has different temperatures, those frequency bands are not going to correlate anymore. You're getting what is called frequency decorrelation, and basically the experiments need to work harder to be able to correct for this. So that's one application that's being, for this technique. And I'm calculating the statistics of the dust temperature map in along the line of sight, and I'm hoping to see something that's kind of helpful to the community. Okay, so far we've talked a bit about the stars and gas and dust, and that was the baryonic component. So time to get to the last component, the dark matter. So there are a couple of fundamental requirements for dark matter that needs to be satisfied. So first of all, we know that it doesn't interact with the electromagnetic field. So this means the particle, if it's a particle, should have no charge. This also means very bad news because whenever we are trying to observe something in the galaxy, we use the electromagnetic field with the telescopes, unless we're gravitational wave observers that use gravitational waves. But basically, this makes it dark. That's why we call it dark matter. And then the other property of it is it has to interact with gravity. So it has to have a mass. And we know this from at least 5 independent astrophysical probes that tell us that this substance exists in the world, that it has mass, and that we cannot see it with photons. So this is very well established and is one of the biggest open questions of the field of physics nowadays. Like, what is dark matter? That would be an amazing thing to learn in our lifetime. The of the possibilities of what dark matter may be is actually quite complicated. And there's many different ways to group these types of models. You can group them by the energy at which their particles are produced. You can group them by the production mechanisms. You can group them by the detection mechanisms, or you can group them by the energy levels themselves. But just as an idea, in terms of the way people are kind of searching for dark matter, one way that people are looking at is like they are trying to see literally production of the dark matter particle. So they are looking at the Large Hadron Collider at CERN in Europe, where they're trying to basically produce dark matter and be like, okay, we produce it from the standard model, we clash together standard model particles, and they produce dark matter and we detected them. The other way is to sort of hope that the dark matter itself is going to interact with direct detection mechanisms like the LOX measurement in the that are normally kind of underground in the Earth, and you're just hoping to basically catch the particle somehow, hope it interacts with your detector, because for certain models this interaction is predicted basically. And another way is what I mentioned before, where dark matter annihilates and produces something in the standard model, like a photon in this case, so gamma ray gets produced, and then you catch it with standard model telescope, like the Fermi-LAT. And then apart from these classes of techniques, there's what we call astrophysical probes. So the previous ones were sort of the classical probes of dark matter that were set up in the last 70 years. In the last 10-20 years, these astrophysical probes have started to get quite a good handle on dark matter as well. The basic principle behind astrophysical probes comes from the idea that we can observe structure formation in the universe with astrophysics, and that structure formation is different depending on the dark matter model, and I'm going to explain that right now. So what we know so far is that galaxies like our own actually form at what we call a node in the dark matter filament. So dark matter drives the collapsing of matter as the universe evolves and creates filaments of it. So this is all dark matter that you're looking at. And at the nodes of these filaments, the baryonic matter also clumps together and creates these galaxies like the one we live in. So this is a video that shows this. This is a simulation. So the lower left side shows the clumping of the dark matter density, and the upper right side shows how the gas density follows it, but with a delay, basically, and coagulates exactly at the spots where there's the most amount of dark matter. This is a very pretty video done by the Eagle simulation, which is a team in Europe, I think. So this is currently basically accepted as the paradigm in which galaxies kind of form. And the very helpful, so this is kind of the a walkthrough of what is happening. We start from the initial conditions that we observe. So basically the cosmic microwave background that has this, anisotropies in it. So it has little deviations from the density being completely homogeneous. And those little deviations, have what we call a power spectra, which is a distribution on the sky. And as the universe expands, that distribution causes this collapse of matter into filaments, into dark matter filaments. And it also creates what I call mini dark matter halos that are gravitationally bound to a bigger dark matter halo. So we call that a substructure or sub-halo mass function. So it's basically these tiny densities of dark matter that are rotating around the main dark matter halo, which is a halo at a node like this. So the connection to the dark matter model comes from the fact that different dark matter models, like cold dark matter versus warm dark matter, are going to create different distributions of the masses of the halos of dark matter in structure formation. So in this case, we see cold dark matter creates many tinier halos around the big halo, and warm dark matter has very much less of those. It's focused on more having chunkier pieces of dark matter together, and it's basically had this substructure erased in the early evolution of the universe. So we normally use this, what we call this halo mass functions, that are functions that describe the amount of like how many of each types of halos are there predicted on the sky for each model. So what do you guys think dark matter would look like on the sky if you could actually see it? Should take like 2 seconds and kind of imagine it. And then I'll show you a simulation. So this is kind of what it would look like on the sky, which I feel like is pretty crazy. So basically we have these filaments out there that we know are there. So whenever you see with a telescope in your backyard, you see one of those tiny galaxies, like you see M87 or 103 or all these Messier objects, they are formed at a halo of dark matter that's a linkage of a network of filaments of dark matter. So you could sort of almost imagine like linking those galaxies together with filaments of dark matter between them, because that's kind of what's happening in the world, which is, just mind-blowing. Okay, so how do we get to this whole thing? To actually characterize dark matter? Well, we are going to use, we can't have dark matter interact with light itself directly, because it just doesn't interact with the photons, but it has gravity, and gravity interacts with light. So this is just a simple representation of it. When you have a photon passing by a very heavy object like our sun, it's going to get bent over. And this phenomena was confirmed, already many times over in many different situations. It's, think also interstellar. That's why in the interstellar, you see the black hole having all that ringing around it with the light stuff. Basically, light is getting bent like a lens around it. So strong lensing by these heavy objects can be used as a probe to actually probe the mass that's doing the lensing itself. So you can use galaxy cluster lensing, but you can also use lensing of a galaxy by another galaxy. So this is a galaxy that we call the lensing galaxy, and there's a farther down the line of sight galaxy that has a quasar in it. And this galaxy is going to create a lens system for this quasar that's going to result in a couple of images of the original quasar. So in this case, you can see there's what we call an Einstein cross happening with four X-ray images of the same original galaxy. Now, the way that the light is actually lensed here depends on the mass of this galaxy, most of which is dark matter, not baryonic mass, right? And it doesn't depend just on the total mass, but also on the distribution of that mass. So all the substructure of the dark matter being kind of placed in the right location is what causes these images to look a certain way. So this allows us to use the distribution of dark matter to learn about the particle of dark matter themselves, because we can reverse the problem and think, okay, now I'm probing the substructure, and I know the substructure depends on what type of particle I actually had originally in the universe. And there's a second part here, which is the fact that along the line of sight, there's actually going to be other halos of dark matter that don't have galaxies in them, because not all the halos of dark matter get galaxies. Like only the big ones basically get galaxies. So those are called dark halos, dark matter halos. But we see their impact when on the lensing image itself. So we can measure these systems, these Einstein crosses, using the GAAC telescope in Hawaii. The GAAC telescope is currently the largest telescope in the world. It has 10 meters. It's been the largest telescope in the world being actually used for science for the last 30 or 40 years. So it's very long lasting. There's a couple of other telescopes that are supposed to come online, but they are taking their sweet time in terms of actually being built. So this guy remains the flagship. And it's actually very good at doing this science. So this is an example of modeling such a system. So we have the observed images and positions of those 4 Einstein crosses images. And what we want to do as a theoretician that's modeling this is we want to model those exact fluxes and positions, but using the over densities and under densities of the dark matter itself. So the blue and the red here in the image represent the distribution of the dark matter structure. And there's a nice computer code that, given each dark matter structure, basically tells me what would be the position and the fluxes of those images. And this is how the data itself looks like. So we have different quad systems. They look kind of fuzzy. That's okay. It still works. And then for each one of them, we do many realizations of modeling those quad systems. We don't do just one. We do like 10,000 for each of them. And then we basically infer what would have been the distribution of the statistics of the dark matter that would allow for these possible quad systems to happen. So there's a specific energy range of the dark matter models that are prone to being probed by this regime. Not all of them can be probed, but the ones that can be probed are in what we call the warm dark matter regime, or the KeV energy regime. And what I did in my research is I used these measurements to eliminate sterile neutrinos as candidates for dark matter. So sterile neutrinos are a type, they were a possible dark matter. They are called sterile because they don't interact with a weak force. Generally, any particle that doesn't interact with a specific force can be called a sterile particle, but they are referring to them just because of the weak force in this way. They are a theorized particle that hasn't been detected ever. But they do fit the bill for dark matter in general. But with this technique, I was able to show that actually most of them, most of the energy range that was available is actually not possible because of the data. So that's basically ruling out. I've also used some other constraints in addition to gravitational strong lensing. You can use galaxy satellite counts. So you use the satellites of our own galaxy, as well as other galaxies. You can count them and say, okay, these guys, they don't have other satellites, and that means you should not be able to have certain halos as well. So it's kind of a different probe, but probes the whole regime. And then you can also use the Lyman alpha forest and combine everything together. So the limits at the time, they were the most precise limits on dark matter in this regime. So basically, these measurements are not being able to be reached by the particle accelerators, because they don't probe this exact specific regime. So it's an independent probe, and it's kind of very useful to combine them together. And another thing I looked at was what would be the upcoming performance for these measurements using the telescopes that are coming online in the future. So one improvement is going to happen at the Keck telescope itself, because it uses adaptive optics to correct for the atmosphere. And they are gonna install a new adaptive optic systems called Kappa, and also a new detector called Iris. And these guys together are just going to improve the measurement. So if you can see here, the bulky thing is the QN measurement. And then the next one is how it would be with the adaptive optics system. And the third one is adaptive optics plus the new detector. And finally, the fourth one that looks super crispy, that's how it would look like when the 30-meter telescope gets built. So what we call the TMT. Now, the TMT is part of a class of telescopes that are being kind of funded right now across the world. The other one is the GMT, the Giant Magellan Telescope. Harvard is pursuing the GMT. Basically, the GMT and TMT are split between different universities. So there's consortium where a bunch of universities got together and they're making the TMT. And there's another consortium where other universities are making the GMT. And also the Europeans, so both of these are in America. And then the Europeans are making the extremely large telescope, very inventive name. And that's probably, that's happening just with the Europeans' budget. But nevertheless, all of these guys put together are really, really going to change the game, because these are right now the flux ratios as they will be detectable by these telescopes. And you can see by the time you get to Iris and Ephemeros are the detectors from TMT. The radio precision on those measurements of those structures is going to become milliarc seconds, which is like, wow, super useful. And the ratio in percentile in the error bars are going to get below basically 0.7%. And that will allow us actually even down to 0.2%. And that will allow us to have exposure times that are very small. So right now we study a system like this with like a 10 to 15 minutes exposure. Back when everything will be online, it would take less than a minute to observe a whole system. And this is really critical because right now we do science using only like 13 different systems. And we only know on the sky of them being like 50 such systems. But the Rubin Observatory and Euclid Observatory, Euclid is already online, is taking data, and Rubin is going to come online in about 3 years. They're going to find thousands of these quad systems. So we're going to have thousands of Einstein crosses to use in our analysis. And being able to observe them very fast with the TMT is very important. So the fact that it's less than 1 minute means we can get all of them in an actual research program. That's very good news for us. And SNOMAS is a report that the particle physics community does every year, or I don't know how often they do it, but they did one last year. And they basically identify the most important areas of research for particle physics. And they really highlighted the integration of the astrophysical probes with the dark matter, traditional probes in particle physics as a high priority research. So that's very good news. And another future addition is that right now the work only takes advantage of the photometry of these images. But if you can see, they also have some structure. They have these extended bananas, as we call them. If we're able to basically measure those bananas, we can get even better constraints on the whole problem. So that's an interesting thing to be pursued right now. And the other thing is that if you've noticed, I described that you have to sort of propagate the evolution of the universe to get at the structure formation, to then sample the data to be able to constrain the dark matter particle. Now, this procedure can be very computationally intensive. It can take months, in fact, for a single dark matter model. And it's not really possible to do this for every perturbation in the dark matter model. So you change the mass just a bit, you need to do everything again. So what we're doing right now is that we're trying to categorize dark matter models into classes in which we will be able to translate constraints from one to the other, so that we can basically clear dark matter models together without having to run these n-body simulations all at the same time. And my undergrad student, Yixin Chen, she worked on finding a ratio and a functional connection between the distribution of the big halos and the distribution of the smaller halos, because getting the smaller halos takes a lot of computational time. It's a non-linear process, and whenever you go into non-linear regimes, that's when it's like bad news. So she came up with an analytical formulation that actually captures the behavior of the halo mass functions for very different classes of dark matter. So this is the form that she proposed, and that it fits basically all of these types of functions. That's very cool. And she also simulated the impact of the 6 main fundamental cosmological parameters that are normally used in cosmology. So she was perturbing all of them, doing these nice, very GIFs, and seeing how the halo mass function here on the bottom changes. So technically, we could even use this measurement to kind of go and verify Planck itself and be like, okay, do we get the same constraints? Even H0 and the sigma 8, which are a big debate in the community nowadays, can be kind of probed in this way. So to summarize, the upcoming decade of cosmology is going to have a couple of big experiments that are coming that are trying to really nail inflation. They will be so precise that they will either discover inflation or basically say inflation is wrong. Is not one of the things that we should consider. So using this dust galactic studies is kind of important to be able to actually clean this maps. But most importantly, it means we have upcoming data that are going to include the emission from dust in very high precision, and we can actually study the galaxy itself. So we can do galactic studies with these measurements. And so a couple of these guys' applications were like the frequency declaration for the CMB experiments, the mapping of the magnetic field, the correlation with the phase of the interstellar medium, and the calculation of the interstellar radiation field in 3D. And then on the dark matter side, it remains the biggest mystery that we have out there on the sky. And researchers have now reached the precision where it's possible to use astrophysical probes to constrain warm and self-interacting dark matter, as well as mixed dark matter models, and even what we call fuzzy dark matter. Well, thank you for listening for that very kind of component-based, all over the place description of our galaxy situation. And yeah, do you have any questions?
Ioana, if that's what your undergraduates are doing.
I'm sorry, say again. I couldn't hear you.
If that's what your undergraduates are doing, what are the graduate students doing there?
I've got a question.
Yep.
Was the three-dimensional map of the thermals done with a parallax of the Earth's orbit around the sun, or the galaxy, the solar system's orbit around the galactic center plane?
Okay.
How did you get that three-dimensional shift?
Yes, the video that I was showing you is a camera moving around 20 parsecs around the sun.
Okay.
So that 20 parsecs, it basically doesn't matter if it's the sun or the Earth. It's just like together is like rotating so that you get the perspective as you see it. Very good question. I forgot to mention that.
There seemed to be more than that one circular part you showed us. There were other circular images in the background.
Yeah. There's
like
one of those guys. Exactly.
Yeah, wow. Very fascinating. Thank you.
Anybody else have any questions online? In the room? Speak up.
So I don't know how well I understood all this, but the image that was shown of what dark matter would look like, if we could see it, and it's the streaks in the sky, that, if I understand, is intergalactically, correct?
Yes.
What would it look like like within our own galaxy, not just with our outside of it? Could that be the dust?
That's okay. That's the thing I'm trying to figure out right now, because
Okay.
there are many models of dark matter, some of which would create waves of dark matter in our galaxy, like just density waves. I mean, some of them would be just homogeneous distribution. So it would just look like a fuzz, like we are in it kind of thing. And I've been asking myself, like, can it just look like the dust also? Because we don't currently actually have any probe that has eliminated that possibility. So we have eliminated, for example, that it cannot be stars. And like it can't be very clumped like a star, and like the stars are just all over the place, like the way the stars are. And the way they did that is that they used microlensing. So like there's searches for exoplanets in our galaxy use what's called microlensing. So you can probe how a star's basically emission gets shifted when an exoplanet kind of goes by, when you're looking at something. But those same studies eliminate the possibility of the dark stars being there, because it's like the lensing system would catch it, and by them not seeing it is like, okay, so it's not stars. But I haven't yet found anything in the literature that could eliminate it being just diffused exactly like the dust clouds that you're looking at right now. So it's a possibility, but I'm trying to find a way to actually probe that, because we need some sort of like technique that would actually be like, okay, no, it cannot be like this. And one way I'm thinking of doing that is using velocity information for the dust clouds. so that you can actually kind of match how fast they are moving in the with the galaxy or some, you know, together. And then if they are not seeing any perturbation from the gravity of the cloud, from the dark matter cloud, and that could be basically an elimination of that idea. But I don't have data that's like precise enough for that kind of stuff.
Oh, okay, so it couldn't just be that the dust is accumulated in certain spots just because of an increase of dark matter of 1% compared to other intergalactic increases?
Oh, it could. It absolutely could. No, that is possible because we haven't mapped the density of the dust from. So like what we know for now is that dust forms from what astronomers call metals, which is anything that's not hydrogen or helium. But those metals get formed in stars having basically cycles of life. So all the dust has been spewed out by some poor star dying before, and technically we think whenever people think about clouds of dust, they just think in terms of like, oh, stars exploded I don't know where and that created the stuff, but they don't account for it yet. They're not like, we don't have any kind of simulation that goes to the point of like, oh, here's how dust clouds are actually forming and falling into place. So it might as well have been dark matter that's actually driving how they are falling into place.
Okay, all right, thank you.
All right, thanks an awful lot, Ioana.
Thank you, Ioana.
Thank you.
Great
Let me know
job.
if you
Thank you
have
very
any more
much.
questions. I'm
Great
happy
presentation.
to
All
answer.
right, it's late, mostly because of equipment malfunctions, so we're gonna let people go.
Thank you for having me.
All
Please
right.
come back.
Yeah.
Thanks, Mike.
Thank you.
Do it again.
We will.
Okay.